Hi, everyone, and thank you for joining us today. I know you are tuning in from different parts of the world. Welcome back to those who joined us in previous webinars. It's good to have you with us again today for this special session. And a warm welcome to those joining us for the first time. My name is Maria Giovanna Sandrini, and I'm Chief Communication Officer at Aquafil, and I'll be your host today. Today's session will be moderated by Celine Khawam, a textile and fashion historian and educator. Her multidisciplinary background in textiles and material culture will bring a valuable perspective to our discussion. She will be in conversation with our distinguished speaker, Professor Ada Ferri, full professor in chemical engineering at Politecnico di Torino. Professor Ferri will explain the key differences between nylon, polyester, wool, and viscose, showing how businesses can navigate trade-offs in technical performance and sustainability. For those who are new to us, this webinar is part of a bigger initiative called the econylacademy, a resource platform to talk about ideas, new best practices, industry benchmarks to push the boundaries and do things better for both the environment and people. Just a few notes before we start. Please use the chat box on your screen to ask questions or share comments at any time. We'll save them for our Q&A session at the end. If you experience any technical issues, please let us know in the chat, and our team will be ready to assist you. Finally, please note this webinar is being recorded. A link to the recording will be sent to all registrants afterwards, so you won't miss a thing. And with that, our introductions are complete. I'm now delighted to hand over our moderator to begin the discussion. Celine, the floor is yours.
Thank you, Maria Giovanna, for the kind introduction, and thank you all for joining us from different parts of the world and contributing to this conversation. I am excited to be here and to moderate today's webinar, which promises to be very informative and engaging. So as Maria Giovanna mentioned already, in this session, we'll go over the pros and cons of specific textile fibers to better understand how to use them in various applications. And at the end of this session, we'll dedicate some time for questions. And to guide us through this topic, it's my pleasure to welcome Professor Ada Ferri, who will be sharing her expertise on fiber science with us. Hello, Professor.
Thank you, Celine. I'm happy to be here.
Wonderful. So to set the stage, let's start with the basics. Could you walk us through the main fiber categories, including natural, semi-synthetic, and synthetic, and explain how they differ from each other and what they have in common, using wool, viscose, nylon, and polyester as examples?
So, yeah, to answer your first question, let's start describing what these fibers have in common. They are all polymers. And actually, they are all linear polymers. It means that their backbone is mainly made of carbon atoms with other elements which are specific to each material, and they make their own characteristics. Linear polymers are particularly suited to be fibers because they are already forms long filaments ready to be spun. That say that they are all linear polymers, there are differences between the different materials, of course. So polyamide and polyester are synthetic fibers produced in industrial plants. Wool is a natural polymer synthesized entirely by nature, and viscose is something in between. It is produced in an industrial plant, but starting from a natural feedstock, which is wool. Wool is wood. Wool is the most complex because always nature is difficult to beat in terms of complexity. It contains a large number of functional groups which are responsible for its reactivity. It's highly hydrophilic. It absorbs up to 30% of humidity while remaining dry. Viscose is cellulose from wood, we mentioned, and cellulose is the most abundant polymer on Earth. It contains mainly hydroxyl groups, which are very happy to make bonds with water. And for this reason, viscose is the most hydrophilic of these four fibers. This is good to some extent because it is pleasant on the skin because of the slight amount of humidity that it carries, but it can also be bad in for some other instance. For instance, it's not suitable for sportswear because it stays wet for a long time or it can burn easily. Polyester is the least reactive of all these materials. Apart from hydrolysis of the ester group, polyester is not susceptible of chemical modification. So it is highly hydrophobic, contain almost no humidity. This is why it feels like plastic a little bit. But on the other hand, it's very durable and it is almost inert. Rather than water, polyester prefers to bond with oily substances because it is hydrophobic. Polyamide lies in between polyester and inertness and reactivity of cotton and wool. So its properties are determined by the amide groups. It can form hydrogen bonds with water, even if it absorbs less humidity than wool and viscose. And this makes polyamide versatile in many applications. For instance, in sportswear, it wicks sweat from the skin without retaining too much time. And it is also good for carpeting, where it is less oleophobic than polyester or, for instance, polypropylene.
Thank you so much. That's wonderful. You gave us a very clear picture of how these fibers differ at the chemical or molecular level. And now to take it a step further, could you explain the difference between a continuous filament and a staple fiber, why that distinction affects the way we use them in textiles, and why it matters for performance applications?
Okay, so being a continuous filament of a staple fiber is something which is not related to the chemistry of the fibers that we have discussed before. It's something related to its macroscopic form. Filaments are continuous, theoretically infinitely long fibers. Polyester, polyamide, and viscose are all produced by extrusion, like the spaghetti through the spinnerets in industrial plants, and therefore they are continuous filaments from the start. Wool and cotton, on the other hand, they are by nature staple fiber with a typical length between 5 to 20 centimeter for wool and 2 to 5 centimeter for cotton. To form them as continuous yarn, they must be compacted together in the spinning process. That said, also the continuous filaments can be cut into any desired length, and this means that polyamide, polyester, and viscose can all be converted in staple fibers for different applications. So when should we use a filament and when should we use a staple fiber? So broadly speaking, filaments yarns are stronger than staple fibers because their strength is based on a long continuous filament chains, chemical chains with billions or trillions of chemical bonds. While for staple fiber, the strength is mainly based on the friction between the short fibers, and friction is much less cohesive than the chemical bonds. So filaments are used when strength is important in technical applications, for instance. One example is nylon filaments are kept long for fishing lines or for parachutes, while for clothing applications, filaments can be cut to staple length, especially when they are blended with natural staple fibers such as cotton or wool. However, there are also some application in apparel, like in hosiery, for instance, or sportswear, where polyester is kept long filament because of the smoothness, elasticity, and luster that filaments have compared to staple.
Wow, that's a wonderful explanation. Really, it makes the difference between filaments and staple fibers much easier to understand. And now, since you mentioned that filaments are usually chosen for strength and technical uses, could you expand on the mechanical properties that make them so strong and reliable compared to staple fibers? And on that note, is it possible to further increase the strength of synthetic fibers?
Yes, where we introduce the concept of tenacity, which is the strength of yarns, which is normally related to the fineness. So this is tenacity. Tenacity is the strength necessary to break a fiber or a yarn, which is measured in Newton or centinewton, related to the fineness of yarns, which is measured in tex. So to give a broad idea, we said that filament yarns are stronger than staple. Staple yarns typically have tenacity in the range 10 to 40 centinewton per tex, while filament yarns, continuous yarns, have tenacity between 20 to 80 centinewton per tex, which is about twice the strength of staple, given the same material. There are some exceptions. For instance, if we consider carpets, wool is often used with good durability, even though wool is a staple fiber. But if the fiber is coarse enough and the yarn is coarse enough, like wool fibers used in carpets, they will be strong and durable. If we, in any case, want to mention to rank the tenacity of the materials, we can say that polyamide is the strongest fiber among the four, followed by polyester, then viscose, and finally wool. It should be noted also that polyester retains its strength when wet, while the other three, polyamide, viscose, and wool, have a lower strength when wet. And this is because water acts like a lubricant and makes the polymer chain sliding easier. So this will make the fiber weaker when it is wet. This is not the case for polyester because it is highly hydrophobic, we already mentioned. It does not absorb humidity at all. That said, that tenacity varies with the same material, especially for synthetic fibers, depending on the processing method, and especially due to the draw ratio, which can highly affect strength. So there should be another slide describing the effect of draw ratio. Yes, here it is. So after spinning, synthetic fibers undergo a process which is known as drawing, which is stretching. During drawing, the filaments are stretched under high temperature to improve the orientation of the polymer chain into the fiber. So more strongly oriented fibers are stronger than less oriented fibers. And the degree of orientation can be tuned according to the draw ratio and in general the process parameters. For this reason, for the same material in synthetic fibers, we can have stronger and weaker fiber given the same material. So for instance, when polyester or polyamide are blended with natural fibers, the strength should be similar to that of the natural partner. So we have cotton-like polyester and we have wool-like polyester. So cotton-like polyester is stronger and less elastic than wool-like polyester, precisely because cotton is strong and less elastic than wool.
It's very helpful to see the clear breakdown of strength and tenacity across different fibers and how this can impact fabric performance. Now, beyond strength, other important properties include the fiber's resistance to wear and its ability to recover its shape after stretching. Could you compare wool, viscose, nylon, and polyester fibers when it comes to abrasion resistance and elasticity?
Yes, Celine, we can discuss also this interesting topic. So, if we compare the fibers, these four, in terms of abrasion resistance, polyamide is the highest rank in the ranking, followed by polyester, then wool, and finally viscose, which is the least resistance to abrasion. And in fact, thanks to its excellent abrasion resistance, polyamide is widely used in demanding applications like ropes, nets, fishing nets, carpets, industrial textiles in general. Polyester also performs very well, even though it is a bit less resilient than nylon, and resilience is the property to spring back to the original shape after being compressed. Moreover, polyester is more brittle than nylon, and so it tends to fibrillate easier, and which means the fiber can be split longitudinally, we can say. Wool has natural crimp, and so it has resilience to some extent, but it is covered with the scales, and these scales can wear off under abrasion. Finer wool wear faster than coarser wool, and this is common to all fibers, of course. And viscose is the least resistant of all four fibers in terms of abrasion. It can show surface fibrillation when abraded. A simple example can make it clear the resistance to abrasion of the different fibers. You can think of an old pair of socks. In the high rub area under the foot, the area of the foot, the cotton or wool fibers into the fabric often wears thin and may even disappear and become transparent. So, but if you look closer at the whole socks, you will see these fine filaments still holding the structure together. And these are the polyamide and sometimes elastan fibers that give socks durability stretch. And these fibers will outlast the worn cotton. Elastic recovery, on the other hand, is the ability of fibers to return to its original length. I think that there should be another slide discussing elastic recovery. Yes. Elastic recovery is the ability to return to the original length after stretching. And also in this case, we have more or less the same ranking in terms of elastic recovery. Polyamide has a good elastic recovery. It recovers almost 100% of its size at about 8% of extension. Polyester also performs very well, even though slightly lower than polyamide. 80% recover at similar extension, around 8%. Crimp of wool also give a good recovery to wool. Wool is quite elastic fiber. It will recover 50%, even with 30% of stretch, which is quite large. While viscose, like cotton, is not very elastic, so it will only recover 30% of its original length, even with a very small stretch of 2%. So these have visible effect, like cotton and viscose garments tend to bag at the knees and elbows because they do not recover after stretching, while nylon, polyester, and wool fabrics retain their shape much better.
Thank you, Professor. That's a very useful comparison of how well these fibers hold up to wear and retain their elasticity. Building on this, fiber durability also depends on other properties and industry requirements like soilability, and stain and flame resistance. Could you describe how wool, viscose, nylon, and polyester compare in those areas?
And durability, general durability. So first of all, we have to distinguish what is soilability and stain resistance. So soilability is the long-term tendency of fiber to get dirty and to hold soil, while stain resistance is the quick, short-term ability to repel staining substance when it is in contact with the fabric. So soilability depends on a number of properties of the fibers: absorbency. Hydrophilic fibers like cotton and viscose stain more easily because many stains are water-based. The surface texture, so rougher surfaces trap more dirt, even like dust, for instance, and electrostatic. So because of buildup of the charge, synthetic fibers can attract dust through this buildup of charges. Stain resistance refers specifically, as I mentioned, the ability to repel a stain, and this mainly depends on the nature of the stain and the nature of the fiber. So hydrophobic fibers resist water-based stain, but they attract oily stains. Hydrophilic fibers, cotton and viscose, absorb water resistant easily, but release also better when washing. So the answer in terms of soilability and stain resistance depends really very much on the nature of the contaminants. For sure, for polyester, we have big and less for polyamide, but in general for synthetic fibers, we have a big problems of odor control. In sportswear, polyester tends to retain odors because it is less absorbent in terms of water, but it can trap body oil, let's say, close to the skin. And so the bacteria will flourish in this condition, and odors can also be difficult to wash out because PET poor wettability. It's difficult for the water to penetrate into the fabric and remove these bacteria. So polyester is the worst in terms of odor control. On the other hand, wool is the best in terms of odor control, also because very often is treated with antibacterial treatment to avoid degradation of wool, and this antibacterial treatment avoid the buildup of bacteria on top of the surface. So wool requires in general less washing than other fibers. Also, wool is covered with these scales, which resist dry soiling quite well. So dust and dirt tend to stay on the surface and can be brushed away quite easily. In terms of flame resistance, these four fibers perform quite differently. Viscose, we mentioned, come from wood. And okay, so it is cellulose, it will ignite easily and it will burn very readily. So viscose is even more flammable than cotton because it is less crystalline and it has a weaker structure, so easily to ignite. Polyester and nylon are thermoplastic materials, so they melt and they drip when exposed to high temperature. And this dripping can be hazardous because it can spread flames to other surfaces. Think, for example, a PET curtain dripping onto a nylon carpet. So the fire will be spread from the curtain to the carpet. Between polyester and polyamide, PET shows slightly better behavior than polyamide. Wool is a natural flame retardant material because of its chemical composition. It tends to char and forms a protective layer on top of the surface rather than melting or dripping. And this char will protect the underlying fibers. If we want to speak in general about overall durability, we must consider number of properties: strength, abrasion resistance, elastic recovery, resistance to soiling, but also other properties such as color fading, for instance. So broadly speaking, synthetic fibers are more durable than natural fibers, but the performance depends on the applications. So for instance, nylon has excellent strength and toughness, but lower UV resistance than PET. This is why polyester is preferred for car seat upholstery, for instance. On the other hand, polyester tends to retain odor, so it will be less durable, maybe in sportswear, for instance. So it's really a matter of the overall performance and application.
It's incredibly enlightening and really interesting to realize how many different factors come into play when we think about durability and performance. It's a complex story. So considering this, how do nylon, polyester, wool, and viscose compare in terms of their intrinsic resistance or inherent resistance?
Okay. This is a very nice question, and I like these two concepts of discussing these two concepts with you: intrinsic and extrinsic complex concept, which depends also on the use. So in this case, we can make a distinction between the properties that comes from the chemical structure, the morphology, the internal bonding. So all these properties is named intrinsic durability. It depends on the material nature. It does not depend on how the material is used or protected. But extrinsic durability is as important as intrinsic durability. Extrinsic durability is the effective so it depends also on external factors, not just on fibers chemistry. So nylon jacket exposed constantly to sunlight may lose color and strength, even though polyamide has a high intrinsic durability. And this is because of the use that we are making out of it.
Wonderful. So besides strength and resilience, sometimes the weight of a fabric, also called gravity, can be just as important. Could you tell us how fiber weight affects performance and why a designer or manufacturer might choose one fiber over another for this specific reason?
Okay, yes, the 4 different fibers are also different in terms of their weight, their density or specific gravity. So if we compare the 4 fibers, polyamide is the lightest with a density 1.13, 1.15 grams per cubic centimeter, followed by wool 1.3, polyester 1.38, and viscose 1.50, 1.52 gram per cubic centimeter. So this difference can be perceived by the wearer. So lighter fibers such as nylon and wool give a bulkier and a hairier feeling for the same structure. So denser fiber like viscose produce fiber which are more compact and heavier, given again the same construction. If we want to add overall comparison of fibers, we can also mention polypropylene, which is very peculiar, which is another synthetic fibers that sometimes can compete in the same environment like polyester and polyamide, because polypropylene is very, very light. It has a density of 0.9 grams per cubic centimeter, which make it lighter than water, so it naturally floats on water. So fiber density maybe is not the main factor guiding the fiber choice. It's mainly a matter of maybe elasticity, tenacity, and so on. but for sure it can influence comfort and endo, especially in garments where weight plays a role in wearability.
It's fascinating how fiber weight can somehow affect fabric comfort and feel, and it's something we don't immediately think about, right? In harsher environments like maritime and automotive settings, fibers face different challenges, including chemicals, UV rays, mold, and even salt water. What should we look for in a fiber to make sure it can handle those conditions?
Yes, we come now to the technical stuff. When it comes to technical applications, normally synthetics fibers are preferred to natural fibers for a number of reasons, including their strength. For example, marine applications of PET and nylon are for ropes, for fishing lines, as we have already mentioned. Nylon is preferred for net and fishing lines because of its highest elasticity and abrasion resistance if compared to PET. But PET is more resistant to UV light and less hydrophilic, so it is preferred, for instance, in upholstery, in boats as well, like in cars. Wool is used in carpets, even in the interior of cruises. However, it is not an application in direct contact with the sea water. There are no applications of wool or viscose in contact with water because they are too hydrophilic for any applications in this field. So in the automotive industry, nylon is preferred for its abrasion resistance, superior abrasion resistance for carpets and mats, while PET is preferred for car seats, as mentioned before. So there are some limited applications of wool, sometimes blended with other fibers for upholstery and insulation in premium car, but wool is more expensive and less durable. There are no applications of viscose in the automotive field, to my knowledge at least. There could be some applications of waste fibers, like in insulation or sound absorption panels in the car, which is normally a combination of material use, including non-woven fiber felt that can come from shredded textile fibers, including also cotton or other type of natural material. For chemical resistance, PET is the most inert, we said from the beginning. It is highly resistant to acidic environment and also to alkaline environment, even though strong alkaline environment can also affect polyester. And it resists well to oxidizing high agent, which is a weak point for polypropylene, for instance. Nylon is a resistance to weak alkali and many organic solvents. However, it is attacked by strong acids, especially mineral acids, and it can hydrolyze if it is in contact with strong alkalis for a long time, and it can suffer after the contact with chlorine. Wool, being a protein material, can be damaged by strong acids as well, like nylon, and severely by alkaline solutions, because alkaline solution dissolves keratin. Also, wool does not appreciate the contact with chlorine bleach because it will produce rapid degradation. Viscose is the weakest in terms of resistance to chemicals. It degrades both in strong acids and alkalis, and also oxidizing agents can cause damage, like fire also oxidizing chemicals can burn the viscose, the cellulose filaments. And it is sensitive to solvent and to finishing chemicals, and it is the least resistance of the group. In terms of biological resistance, this property is mainly related to the ability of a material to absorb humidity. So polyester does not absorb humidity, so it has the greatest resistance to mold growth, which mold is a type of fungi. Nylon is quite resistant, even though it can support the buildup of some mold because of its 5% moisture content. Wool can be attacked by mold, especially in warm and damp conditions, but the least resistance also in this case is viscose, because cellulose is a good nutrition source for fungi, and so it is the least resistance of all four.
That's very insightful. Now, shifting from durability to daily applications, could you explain how these differences affect comfort, moisture management, and the hand or the feel of the fabric? Is, for example, one fiber better than the others, or does it depend on the specific use?
Okay, now let's go with comfort. After the technical stuff, yeah, we had this, sorry for skipping this slide, which was summarizing the resistance to chemical and mildew. So you can give a look at now, but we have already discussed about this topic. So we can go with the next one, which is comfort, moisture management, and hand feeling. So in this field, the natural materials give their best. Wool is very good as for thermal comfort, is a very good thermal insulator in mild to cold environment. It can insulate the body and still be breathable. So being able to absorb up to 30% of moisture without feeling wet, it retains its insulation even when the environment is quite humid. It is soft and springy and luxurious, especially if high quality merino wool is used. But on the other hand, when it is wet, it takes a long time to get dry, so no good for sports where you sweat a lot. Viscose is soft and smooth against the skin. It drapes well. It has excellent absorbency. It has a silky, smooth, and cool end, so it is good especially for warm environments. If we compare synthetics, nylon is generally more comfortable than polyester. Nylon can be soft if it is brushed. It is smooth and silky, and because of its medium moisture regain, it reduces the plastic feeling that we have with polyester. Polyester is hydrophobic. It can be quite uncomfortable, especially in warm environment, and it has the least pleasant hand. Even though we have to say that finishing put on top of the fibers can affect the hand very much. So the end can be changed also for polyester by adding softeners and other chemicals to make it more comfortable.
And on that note, nylon and polyester are often mentioned together. And from a material engineering perspective, what are the key differences between nylon 6 and polyester that designers, specifiers, and engineers should know to make the best choice for a particular product?
Okay, so most of this we have already discussed because we have already discussed most of the properties. So polyamide has some key strengths, which is toughness. It has the best abrasion resistance and resilient and high durability. So it is used for high demand applications, carpeting, ropes, fishing lines, things that we have already mentioned. Polyester is also good in terms of it has good strengths and excellent UV resistance, and it is easy to recycle. So it has a wide variety of uses: apparel, sportswear, automotive interiors, outdoor gear. So if we want to have a complete pictures of synthetic fibers, we can also mention here polypropylene. Even though it has a smaller market share in fibers compared to the giant polyester and also to nylon, we already mentioned that polypropylene is the least dense material, very light, and it is very hydrophobic. The other point that we have not discussed is that it is actually the weakest among the three fibers, polyamide, polyester, and polypropylene. So because of these properties and because of the low cost for polypropylene, it can compete to polyester and nylon, especially in disposable, mainly non-woven or geotextiles, where cost is a limiting factor. So if we want to mention also polypropylene, it has low cost, basic performance, ideal for disposable, non-wovens, and so on.
Very enlightening once again. Now, moving to another key topic, circularity, could you explain the differences between mechanical and chemical recycling and which polymers can be restored to virgin-like or near original quality?
Sure. This is a really big topic, and we are heading towards the end of this webinar. So we will give a brief overview about recycling and afterlife. There are actually three types of recycling processes. The first one is the mechanical recycling, which exploit physical force to shred the fibers and open the fibers, which then can be spun again into yarns. The good of it is that it has the lowest energy consumption, but it has a big disadvantage that it can damage the fiber to a great extent, making them shorter and weaker. So sometimes you cannot respun them into yarns, and so you have to go with downcycling. Second type of recycling is thermomechanical. So in this case, heat is used to melt the thermoplastic polymers to reform chips and then from chips to fibers. So this is the common way that is used to recycle polyester bottle, PET bottles into fiber. But this thermomechanical process is not yet established for fiber-to-fiber polyester recycling. And this is because thermomechanical recycling is strongly affected by the contaminants that can be present in textile polyester. So contamination will make it more difficult to apply thermomechanical. So on the other side, nowadays, the use of bottles to produce fibers is debated because we are moving bottles from the closed loop of packaging, moving into the open loop, the open economy of fibers at the moment, and also because there is shortage of PET bottles, recycled PET bottles that are used mainly by the packaging industry. The third recycling process is the chemical process, and in chemical recycling we can distinguish two types of recycling: polymer recycling, which means that a solvent is used to solve the polymer and then reform into fiber, or the monomer recycling. In this case, it is a strongest process in which the polymer is chemically broken down to its building blocks, the monomers, and these building blocks there are used again to create a new fiber, high quality. It can restore virgin-like quality because we go back to the original monomers. And this is the big advantage of monomer chemical recycling, but it has the disadvantage that it costs a lot of energy, and the amount of energy that is required must be compared to the virgin case, so through an LCA analysis.
Thank you so much, Professor, for outlining the pros and cons of recycling methods. It's such an important topic to be aware of, as you said, especially when we think about designing with purpose and considering the product's end of life. Now, looking ahead, what advances should we expect in textile material science to enhance circularity and performance, particularly for nylon? And do you see any improvements in existing polymers or the emergence of more bio-based fibers? And how significant will design for disassembly be in this context? I know it's a long question, but...
Yes, yes, this is also another super interesting topic. Don't remember if we no, we don't have a slide for this, but we can discuss it. So if in the future we will stop using the oil in general for energy, so most of the oil that we are extracting now is for burning into engines and to produce mainly electricity or for cars. But if in the future we will stop extracting oil for energy, so other feedstocks will have a better chance to take the stage in polymer production. So at the moment, part of the oil, a small percentage, is used for polymer production. But in case we are not using oil anymore, we can use other feedstock. So that could lead to an increase in bio-based polymers. So polymers that they are manufactured starting from vegetable feedstock rather than oil. And today they are just a few percentage of the overall plastic and fiber production. Also, agricultural waste could become an important source of plant-based feedstock for bio-based polymer. So the latest data of life cycle assessment of bio-based fibers suggests that if we move to vegetable feedstock rather than oil, this will reduce the CO2 emissions in the process. And in the same way, if we use recycling as a feedstock for producing new fibers, even though with the monomer processing, this will also reduce we will save CO2 emissions. So in terms of being more sustainable, agricultural waste and chemical recycling can help a lot. When it comes to your latest question to circularity, the challenge is that most textile and apparel products today are not designed to be recycled at the end of life. And the biggest barrier in this field is fiber blends. So once that the materials and the different fibers are blended at the fiber level, they cannot be separated mechanically. So only chemical recycling is possible. So at the moment, we don't have enough data to assess how sustainable the recycling process really are. And so beyond the technical feasibility, all these recycling process should be evaluated for energy efficiency and for cost also, which financial sustainability is also a big issue, of course.
Well, thank you, Professor, for those wonderful insights. We've learned so much from you today. I see that we have a few minutes left before we conclude this session, so I'd like to open the floor to questions from the audience. We received a large number of excellent questions, so if you don't have time to address them all, we will follow up afterwards via email. So let's begin with the first question. Are synthetic fibers toxic? Could you share your perspective on this from a scientific point of view?
Okay, so this is a statement that is has been around for a while. So my point of view on this point is that we don't have any scientific evidence to claim that synthetic fibers are toxic. Actually, we have scientific evidence for the opposite, because both polyester and polyamide are classified as biocompatible. Polyester is used to produce stents, so vein replacement. For instance, polyester dacron is one type of polyester which is used for stents and vein replacement and can be implanted into the body. Nylon is used for suture, for catheters, for tubing. So in all these applications, of course, specific grades are used where all additives are bio-based, and there are specific standards like ISO 10993, which assess the biological evaluation of medical devices. So we use the same materials, more or less the same materials for producing fibers. Normally we use PET bottles to drink, and we use this same bottle to produce polyester fibers. So as we discussed before, these polyester bottles should not be used only for fibers, because they are used for bottle-to-bottle recycling, and we should push more on fiber-to-fiber recycling. So at the moment, we cannot say that synthetic fibers are toxic. They raise concerns for their low biodegradability. This is true. So they will stay for long years into the environment if they are dispersed into the environment. But this is very different with respect to toxicity. It's a matter of biodegradability, not biocompatibility.
Thank you, Professor, for addressing the misconceptions around synthetic fiber toxicity. I think it's, you're right, it's a concern frequently mentioned in online sources more specifically. We have another great question that was raised by several audience members. Can you share your thoughts on microfibers? Are they exclusively released by synthetic fibers, and can higher durability or abrasion resistance help reduce their release?
Yeah. Microfibers and microplastics is another hot topic today. So we have to say that all fibers shed tiny fragments when we wash them, but also when we use them by rubbing fibers together. They will release small particles, small fragments of fibers. So, in fact, most of the fragments in a laundry cycle, according to the scientific evidence, comes from cotton garments rather than synthetic fibers. But the key point is that natural fibers are not considered microplastics. So microplastics are only those coming from synthetic fibers. So cotton shredding from a textile is not considered a microplastic. So for sure, washing machines is a major source of microplastic pollution in the ocean, for instance. Many studies are going on, many data are published today. These data have demonstrated that clothes that have the fluffy rice surface, like the fleece, tend to release most fibers. And so in order to reduce emissions of microplastics into the environment during a washing cycle, we should avoid this type of finishing that create a pile surface in the first place, or we should make the fibers more resistant to abrasion. Another big source of microplastic emission is carpets. When we move on top of carpets because of the continuous contact and mechanical impacts, we have the release of microplastics. In these regards, the better abrasion resistance of polyamide, if compared to polyester, suggests that polyamide should release less microplastic than polyester. As mentioned before, polyester is more brittle, it can fibrillate, and it can release microplastics easier. So on top of polyester being piled and brushed for more surface pile.
Thank you, Professor. We have 1 minute left, but perhaps we can ask the last and final question. How does nylon compare to polyester and other synthetics in terms of shedding?
As I mentioned just 1 minute before, is that the data are being produced in these days. We have some data, but there is still work to be done in this field. We don't have a full picture of how much different fibers release. For sure, what has been demonstrated that the more airy the fabric is, the more microplastic it will release in the environment. So, you know, these microfibers are made in polyester, very soft, very hairy. This is the most emitter, let's say, of microplastic for sure. But more data are going to come to confirm.
Perfect. I believe we're running out of time, but rest assured, we'll follow up with answers to the remaining questions. Once again, thank you so much, Professor Ferri, and to everyone in the audience for joining us today. And thank you to the Aquafil team for organizing this webinar.
Thank you, Celine. And here we are, and we are at the end of our session. So first of all, a huge thank you to our incredible speakers, Professor Ada Ferri and Celine Khawam, for sharing their invaluable expertise with us today. And of course, thank you to all of you in our audience for your time and your interesting questions. We hope you found the discussion as insightful as we did. If you would like to dive even deeper into this topic, keep in mind that over the next few weeks, we'll be releasing 2 new podcast episodes directly connected to today's sessions. To make sure you don't miss them, please visit the Academy News section on our website, econyl.aquafil.com, or subscribe to our newsletter for all the details. A link to the recording of this webinar will be sent to you in the coming days. Before you go, a quick request. Immediately after this webinar ends, a pop-up window will appear with a few questions about this session and your interests. Your feedback is incredibly important to us, as it helps us organize future topics that are truly relevant for you and your team. On behalf of the entire ECONYL team, thank you once again for joining us. We look forward to welcoming you to our next webinar. Have a great rest of your day. Thank you.
Thank you very much. Goodbye.
Thank you. Bye-bye.
Bye. Bye. Bye.